team, and Raham Sendagide is my name. Hoping all of us are doing great. Today, I'll be taking you through two major things. To begin with, I'll be showing you how we implement a stack using a linked list, and also I'll be taking you through how we can implement a queue using a linked list as well. Well, maybe to briefly take you back on what a stack means, you realize that a stack is where we add and also remove elements from only the top. And this makes a linked list the best data structure for implementing a stack. Well, in this operation, we actually have about four operations in here. That is to push, then pop, get top, and finally is empty. So I'm going to be talking through each separately. So to begin with is the push. So the push operation, you are generally pushing an element onto the stack. This can also be seen in a linked list because it simply indicates that you are actually inserting a new node in a linked list, which also has a time complexity of 1:1. When we move to the pop, this simply means popping an element from the stack. So in a linked list, we are actually removing the first node from a linked list. So this also has a time complexity of 1:1. When we move to the get top, this simply means removing the top element from the stack. And also in a linked list, it means you are returning the stored data in a node. Okay, so this operation also has got a time complexity of 1:1. Finally, we have what we call is empty. So is empty operation, we are looking at emptying a stack, and this basically means that the head or the tail of a linked list is actually null, and therefore you are updating the head pointer. So this also has a time complexity of 1:1. Well, so this very juncture also allow me to take you through the implementation of a stack, of a queue using a linked list as well. Well, this has got four operations. We have a queue, we have an enqueue, we have dequeuing, we have size, and then finally we have is empty. So when it comes to a queue, we are actually adding and removing elements from the end and also adding at the start of So we have four operations in here. First and foremost, we have what we call enqueue. So if you are enqueuing, meaning that uh, you are adding an element to the end of the linked list, that means at the tail of the linked list. Then this has a time complexity of 1.1. And when it comes to the queue, it means that you are actually removing at the front of the list, which also has a time complexity of 1.1. Then when it finally comes to size, here you are basically looking for the size of the queue. When it comes to linked list, we are simply uh, reversing or traversing the linked list and then count the number of elements in the list. Then finally, when it comes to is empty, it means we check if the queue is empty, and if both the tail and the head of a linked list are empty, we therefore refer them to be ignored. So in a brief overview of all this, actually implementing the stack and a queue using a linked list has got a very efficient time complexity when it comes to implementation compared to an array-based implementation, which brings about higher degree of complexities because it involves resizing and shifting of elements, especially when it comes to insertion and deletion operations. Well, thank you so much for listening to me. Catch you later. Have a good day.